just a few notes on some of the review problems. I'll go backwards somewhat, cherry pick some things. How about 1016 number 11, Green's theorem problem. The integral over the curve of f dot dr, and this is they're both vectors, so let's bold them. And this is, the book doesn't tend to do it, but I'm going to emphasize, hello, oh well, can't do it. I was going to change this into the closed curve symbol, closed integral symbol, but that's okay. So this is the integral of, so our vector field is root x plus y cubed, and then x squared plus root y. Ooh, I don't know why that turned green. Okay, so this we could also express, if we wanted to, we don't always have to do this, as root x plus y cubed dx plus x squared plus root y dy. Okay, and we now want to think about how a Green's theorem apply. Well, first we need to know the curve. Okay, the curve is sine x from 0 to pi 0. So let's just have this thing graph sine x for me. 0, 0 to pi 0. Really don't need such a big picture. So, well, okay, so let me just modify it a little bit. And let's just go from 0 to 4, let's say. Okay, so here's our sine curve. 0, 0 to pi 0 along sine x, and then back on the sine line segment from pi 0 to 0, 0. Now notice that is clockwise. That's the negative of the usual orientation for the boundary. Okay, so this curve is the negative, so I'm going to take the negative of that, and then the negative of that is actually going to be the boundary of the region, and then that region is going to be in here. Okay, now we can use Green's theorem. That turns into a double integral over R of the scalar curl of this vector field. So you take, this is P and this is Q, you take dq dx minus dp dy, and the nice thing is that the roots cancel it, they just go away. Anything that's only a function of y in front of the dy, and anything that's only a function of x in front of the dx, will always die when you do a Green's theorem calculation. It's a really powerful thing. So I still need the minus, which I just almost forgot. Okay, and so then dq dx is going to be 2x, and then plus 3y squared. Oops. And then dA. Okay, and then we just have to set that up. And so that's going to be 0 to pi. And then, so that's, I'm setting it up as a dy dx integral because it makes sense, because we know y as a function of x for the top, the upper boundary of this, and then y for any given x goes from 0 to sine x, and then it's just going to be this integrand. Okay, and that's not too hard to calculate. Well, let's see. We're going to get, yeah, so the 2x dy, that's just going to give us, well, it's going to give us 2x sine x, I guess. And then 3y squared is going to give us y cubed, so it's going to give us the sine cubed. So it's going to be a certain amount of integration to do there, but I think I'm going to skip that. The main thing I wanted to show you is just how the steps of Green's theorem would work, and in particular getting the right sign from the orientation. They do, right before this problem, they say be careful with the orientation, and this is why. Just because you have a curve that goes in a certain way, just because it's a closed curve, doesn't mean that it is going around in the right way to use Green's theorem without flipping the sign. Here we did have to flip the sign. Okay, now what's another one? That's good. Let's look at 1053. Let's say number 21. 1053, number 21. And so we've got f of xy vector field is 2y to the 3/2 I plus 3x root yj. So we are asked to do a work calculation for this. This is a force field, and we want the work done in going from P to Q, which is P, which is 1, 1, to Q, which is 2, 4. And they don't tell us the path. Oh, well, that's interesting. The only way this makes sense is if this is a conservative force field, so that that's path independent. And let's check that. If we're suspicious, we just take, we take dq dx, and we see is it equal to dp dy. Alrighty, let's see. Let's put a little question mark there. Question mark. Okay, well, let's calculate both sides. dq dx is 3 root y, because q is the j component. And let's see, is that equal to, yep, 3 root y is dp dy. And for some reason it doesn't like to equal, it doesn't think that equals deserves to be equalized with. Interesting. Is it going to work now? Weird. Okay. So it does work. So this does look like, now remember, that's not a guarantee. Not a guarantee in itself that this is conservative. That was the trickiest bit. For example, the vortex vector field, where you take a point out, that's not conservative. But let's see. If we go from 1, 1 to 2, 4, are we necessarily being in a region that wraps around a hole where this thing is bad? Well, this thing is bad where y is equal to 0. In fact, where y is less than or equal to 0. But the domain of definition and niceness of this thing is everywhere where y is greater than 0. That is a simply connected region. It's a half plane. There's no holes in it. We can't go around something and get into problems here. And so the precise version is going to guarantee it. So since f, I'm going to not bold it, is nice on the simply connected region, where y is greater than 0, we're okay. It really is conservative. Now, of course, we could have shortcut that theorem, and we need to find a potential anyway. And if we can find a potential, then it's really going to be okay. So we just find a potential, and so what do we need? We need something where the partial of the potential f with respect to x should be 2y cubed, 2y to 3/2. Okay, so let's find that. Oh, well, this one's pretty guessable, I have to say. F of xy, that's a constant as far as x is concerned, so it's just going to be 2x y to the 3/2 plus a function of y to be named later. But then I just check, well, given that more precise version of f, what is df dy? That's then going to be 3x root y plus g prime y. And that's supposed to be 3x root y on the nose, and that just means g prime y doesn't have to be, it can be 0. So g prime of y has to be 0, and so g of y can be a constant, and we don't really need it to be any other constant but 0. So this works. It's not the only potential that we could use, but it works. And if I added a constant, what I'm about to do is I'm going to evaluate the potential at these 2 points and subtract. So just like with the regular version of FTC, adding that constant in for a definite integral doesn't really matter. Okay, so the integral over the curve of, I'm going to steal it from up here because the bolding and everything takes a while, of f dot dr, that work integral, is going to be just f of 2, 4 minus f of 1, 1. And so that's just going to be, this is our f, it's right here, the g of y was 0. And so it's just going to be 4 times 8. That's 2 times 2 times 4 to the 3/2 minus 2, which looks like 30. Hopefully that's the right answer. Okay. And let's see, this video is probably already getting a little long, but it might be good to, oh yeah, let's just look at one on scalar line integrals. Let's say 37. I know people have trouble with that. I did talk about that in another video, but let's just do it again. 1043.37. We have these scalar line integrals to define the moments of inertia of a wire. That's going to be the integral, the scalar line integral over this curve of y squared. And again, they use rho. I guess I use rho because it's in the book, but it's just silly. It should be lambda. It's a linear density. So you take the density times ds, which really, this whole thing combined, you could just call dm. It's a little bit of mass along the curve. And we're just integrating y squared dm. So let me just write it that way at first. The integral of this quantity, y squared, the square of the distance from the x-axis, just like with moment of inertia for like a lamina or a solid object, times dm. And the problem with that is it's a very abstract or kind of symbolic concept, and we need to convert it into a more practical thing. Well, the first stage is to convert it into density times ds, and then the real practical thing is you're going to take y of t squared for a parameterization times that density evaluated in terms of the t's, and then the big old ds dt, that's going to be the speed, which is this often fairly nasty quantity, times dt. So, for example, we've got the wire in exercise 35. It's a helix. So there we've got xyz equals 2 sine t, 2 cos, not socks, 2 cos t, 3t, and 0 to 2 pi. Okay. And then so x, this is very much like the other video I did from here on in, really. X prime, y prime, z prime, which are going to go into here. Now, it's a three-dimensional version of this guy, but you get the idea. Oh, yeah. Oh, that's why I started reading the wrong thing. This is going to be a more complicated case. I thought it was weird that they switched to 3 dimensions at the start. Okay, so it's the wired example 3. And, oh, I knew that, and I just spaced it. Yeah. It's the semicircle. And the linear density, oh, yeah, okay. So, okay, so example 3. We've got the semicircle of radius 1 with y greater than or equal to 0. That makes more sense for this thing. And the density is proportional, and I'm just going to use the proportionality constant to be 1, to the distance from the line y equals 1, so that's just going to be 1 minus y. Okay, so we're going to get the integral. Let's see, the parameterization is going to be 0 to pi, and t, it's just going to be cosine t sine t, so let's write that down. xy equals cos t sine t. And now just x prime, y prime, that's simpler. But again, the three-dimensional isn't different at all. It's just one more variable. Minus sine t, cosine t. And so the speed, thank goodness, that big square root is 1. That's the really nice thing about the circle. You can parameterize it easily with unit speed with known functions. And so here we're going to get y squared, which is sine squared t. That's this part. Times 1 minus y. That's this part, the density, times 1, I'll even put it in there, for the speed dt. And of course the kicker is often that this thing's nasty, and sometimes we just do setup and do not evaluate because it just gets so nasty. There's no point in trying to grunge through the integral, and sometimes it's impossible. And so that's not a super hard integral to do. You pull out our powers of trig function kind of integration, and that's how it would end up. Okay, good place to stop.